Good day, welcome back to the headquarters. I wanted to take you through some examples of your steam tables. So the other day we went through our phase diagram. This is temperature. This is enthalpy, which is simply kilojoules per kilogram. Or it's your Q, your heat added, per unit mass. Because everything we do with steam is per unit mass, per kilogram. All these units are per kilogram. Okay, let's go through a couple examples. So in your steam tables, you'll have pressure. These are called saturated steam tables. There's also another steam table called the superheated steam table. Superheated region, saturated regions. So over here, we're saturated liquid. Over here, we're saturated vapor or saturated gas or saturated steam. This region is our sensible heat. That means it's sensible because as we pour more heat to it, we see or sense the temperature actually increase. During this region 2 to 3, as we pour more heat to it, we don't see the temperature increase. We shift over to the right under constant temperature and pressure and that just converts, all that energy goes into the phase change of converting that from a liquid to a steam. And then this portion is our superheated. We're completely dry at this stage, right here at state 3. Anything else here, we start to see it. It's almost like sensible again. We actually see temperature increases. Okay, in our steam tables, we'll have pressure, we'll have temperature, we'll have our specific gravity. Be very wise that these are times 10 to the 1,000. It's not given in your table, but that's what it is. Meters cubed per kilogram. Then we have our internal energy, kilojoules per kilogram, and we have them for the F state, which is all this line. We have them for the FG state, which is all in the dome. And we have them for the saturated gas state, which is all over here. Same thing for enthalpy. Okay, so let's go through a couple real-world examples of how this works. Okay, I just want to give this all to you visually. We'll often be asked to convert with steam tables a water to a steam. So we'll be given an initial temperature. We'll be given a final pressure. And we'll be told at that final state that we are a saturated steam. Okay? So what does this look like graphically? I always draw my diagram for the individual cases. This is temperature. This is enthalpy. Here's our dome. I always draw my constant pressure line. Ooh, that smoothened out on me. Okay. So now let's have a look. We're at a water state, so we know we're somewhere here. And we heat this sucker up, and we eventually turn it into a saturated steam. Well, I know that saturated steam is over here, so that's my third state. So these lines always go up here, and all the pressures exist over here until some point that they boil. Then we cross over, and we go up in our superheated region. Okay, so what do they want to know? They want to know what heat is required to do that. So this will be our state 1, this will be our state 2 up here. How much heat is required to do this operation? Convert this water to steam, saturated steam. So basically they're asking how much heat? They're asking H3 minus H1. And they'll also ask, often, as a kind of a little trick or a confusion, what is T3? Meaning, what is the temperature at that saturated state? Okay. So that T3 is easy. We know these are saturated tables, right? So we use pressure for this. So I'll go to this pressure. This whole operation I know is taking place at this P3 that they gave us. I'll go to that pressure and I'll go over and I'll see what temperature that's at. So I know these P and T's, pressure and temperatures, all take place, because these are saturated steam tables, all take place at this saturated curve. So what pressure I'm at, let's say it's 500 kPa, that temperature will be right here. So I know that T3 equals T2. So I can find T2, therefore I can very easily find T3, because I know the temperature stays constant throughout here. All the extra heat that we pour in goes to the phase change from liquid to gas. Therefore I know this is constant temperature. So my T3 is easily found using the pressure of saturation. Okay, what about H? Let's find H3. Again, I just kind of told you that I know this enthalpy is be at a certain pressure. So I've got a temperature and I've got a pressure. What am I going to use to find? I could use either, but I know these are at the saturated point, so I can get my pressure from here at part 2. So I know my pressure. It was the same one I used to find T3. And I can go over, because I know I'm all the same pressure here. So I'll use pressure to come over and look for H3 on the G. So I'll look under this column here. So I'll use pressure again. I will not use temperature. Now H1. How am I going to find H1? If I use pressure, I'm going to get H2, but I want H1. Well, I know this is sensible and latent heat, so every bit of H I pour in, I get an increase in temperature. So the only variable I do have is temperature. So to find my H1, I use temperature. Often people mistake these, because I'm using pressure to find these, but we know that all the pressures exist here, all along this line, and we have only one temperature. So every bit of heat I pour in, I get a corresponding temperature. So that's my only variable I want to know. Okay, so that'll make more sense as we go through some further examples later on, but I just want to take you guys through this graphically for now. Let's go through another example. So this is a common one too. We will have a saturated steam, and they want us to turn it into what? A superheated steam. Okay, often we will be given very little. We'll be given P1, so our initial pressure conditions, and we'll be given T2, our final temperature. And this will actually be given as superheated. So like we're 50 degrees superheated. So it adds a little more confusion. How do I represent this graphically? Let's do that. T, H. So I know that I'm a saturated steam. That tells me I'm right here. And I'm a superheated steam. It tells me I'm right here. So I've got state 1 and state 2. So what do they want to know? They want to know H1 and H2. And H2. Okay, fair enough. So how are we going to find that? Are we going to use temperature or pressure? So if I look at H1, how am I going to find that? On these tables, am I going to look it up using temperature or pressure? Well, I know that H1 is at this pressure, and I know this whole operation is taking place at a constant pressure. Whenever they don't tell you anything about pressure, you always assume it's taking place at some constant pressure. In order to change the pressure, you'd have to do something else to it, and they'll tell you that. So saturated steam, we're given a pressure 1. I go to that pressure 1 up to my tables here. I go over and I know I'm saturated, so I'll go over here to this column. So for H1, I will use pressure. Okay, how do I find H2? What do I have over there? I have a degree superheated. So there's a third table. Your first table is pressure and all these variables like you see above. Your second table is just swaps the pressure and the temperature, so you have better numbers to work with. Your third table is your superheated tables. So that's everything out here. Anything in here will not exist in the superheated table. So we use pressure and temperature. Because the superheated tables have both. So we'll go through an example of those superheated tables at a different time. So, but I really want you to realize that in these equations, in these situations, P1 equals P2. And above here, P2 equals P3. All these operations take place at constant pressure unless they tell you otherwise. Okay, let's do an example that includes quality. So we'll be given a steam. Let me get things right here. A steam. And we'll be given a dryness factor. Fraction, we'll call it. What information will they give us? They'll typically give us a pressure 1, and they'll give us our percent. So how do we represent that graphically? So really, in that case, they really don't need to give us a bunch of information, and we can kind of get where we want to be already, which is nice. With very little information. We know this is T, we know this is H. So we're told we'll draw in our constant pressure lines. And we are told that we are at some sort of percent dryness. So how are we going to calculate our H? Are we going to use a temperature? Well, I'm not given a temperature. All I'm given is pressure. Well, I know this pressure all takes place at the same pressure. That's the constant pressure line. So what am I going to use to find it? I'm going to use pressure. Simple as that. So in this case, it'll be a little different. I will use pressure, but it's different at what H I use. So remember we had our HF plus our HFG. Well, so we're going to use pressure. Let's get that up there. Wish I could spell. Now we need to use the equation. Our H will equal HF plus some percentage of HFG. That's how that equation works. So we know in this equation we're somewhere out here, and it's some percentage of it. So it'll be HF plus some percentage of HFG. Okay? And a final example for you to drive these points home. We will do a simple boiler. So we have some sort of feed water. We'll go through a boiler. And they'll want us to turn it, of course, to steam. So we'll be given initial conditions. And we will be given the percent of that steam. So how do we draw this graphically? We draw our dome. We draw our constant pressure lines. Okay, I know where state 2 will be. Of course, there. We know where state 3 will be. We always just mark those up. That's oh, you know what? That is incorrect. State 3 is not there because we've been given a quality. Darn it. So we actually know that state 3 will be within the dome. Don't we? Okay, now sometimes I'll get in question like, where's my state 1? Am I up here? Am I putting an extra number in there? Or is my state 1 down here? So what I've got to do is I've got to look at these tables and say, okay, well, am I given a pressure along here? I am. And it's P1. And I know these are constant pressure lines. So if I look at my P, this whole operation will take place at that pressure. That boiler operates at that pressure. So I'll look at that P and I will find the information I need to find. Okay? So now what I got to do is find out if this 1, the state 1 is down here or whether it's up here. So and I can easily find that out. So I know it's given at some temperature. So if I go up to here and I find out what that boiling temperature, let's say it's 500 kPa, so that's my pressure, I should be somewhere above 100 degrees Celsius. If this is 40 degrees Celsius, then I know we're down. I know I've got to take it up to that temperature first before it boils. I got to get it up to its boiling point. So I just want to check that there's a difference between 1 and 2, and I will find that here. I'll look at the pressure, and if I'm lower than that, I know I'll never be higher than that. Not for these initial conditions. If I'm lower than that, I know my 1 is below here. So don't hesitate to give me a shout if you don't understand what I just went through. It's kind of hard to explain. So in this situation, this is a very unique one, and it's kind of a trick question, and it's a nasty trick. So what they'll ask is, what is the internal energy change to pull this off? So if we applied what we did before, we'd use that pressure to find our H3, and we'd use this because we've got some percentage, which they gave us here. Okay, so I can find H3. I can also find U3. I'll use that same pressure to find my H2. Now my H2 will be at some pressure, and it'll be the F because I'm 100% fluid at that point. But my H1, I can use temperature to find that, just like we did above. However, I can't do that for internal energy. So I'll just draw you a little chart here, and this is a trick. It sucks, but it makes sense. It's just these diagrams get too difficult to draw all this out. There's limitations to a 1D diagram, so they don't really put internal energy. You got to remember that internal energy is calculated. So I can use temperature to find my H1. I can use pressure to find my H2, right? And in this case, because I'm dealing with quality, I can use pressure plus the this formula up here, my dryness fraction, to find my H3. So I can do that with enthalpy, no problem. I can even do that with specific gravity. But remember this, you can find internal energy 2 with the pressure, find internal energy 3, but you cannot find it for U1. Doesn't work. It's because these other variables, enthalpy, pressure doesn't affect temperature, okay? Not in the case of a fluid. Specific volume, essentially fluids are incompressible. Do you know what I mean? So a steam is well compressed, but a fluid is essentially incompressible unless you're talking super high pressures, and that's not the range we're talking in. So you can find that. So pressure doesn't affect that. Pressure doesn't affect our temperature, but pressure does affect our internal energy. So remember this little chart I drew for you. This one will come on your exam. It will be a trick. And what it comes down to is that formula you've seen in your books, U plus PV. So in order to calculate We'll rearrange this formula. In order to calculate the internal energy at point 1, it does need to take into account pressure. And you calculate it with this formula. U equals H1 minus PV. So we can get this, we know how. We can get this, we know how. That pressure is given. All right, that's all. I hope you guys get a lot out of these visual diagrams. This is a general overview and a graphical method of doing this without getting into the numbers. It's just a lot quicker way for me to bring this all to light to you. And we will go through each individual example of these and we'll work through them with numbers at a later date. So take care, and I will see you again.